All right, so here we are going to do this word problem here. And so just take a moment, read it, get a sense of what's going on. And pause it.
If you need to.
If you need to. All right, so when we look at this problem, we got sample hydrogen, oxygen, total mass of this number here in kilograms, 10 to the negative 15, so that's not very much at all. The hydrogen atom has this mass, an oxygen atom has this mass, and the sample has this quantity, this number of oxygen atoms. And we're asked to convert this number here, which looks like it's the total mass. This is the total mass to grams. Okay. Oh, right, because this is kilograms. These ones are grams.
Okay.
Okay. And then write an equation to represent this problem and how many hydrogen atoms in this sample. Well, let's do this conversion factor right off the bat. Okay. Well, one thing that I know, because I once upon a time took science class, I know that 1 kilogram is equal to 1,000 grams. Okay?
Okay.
Now, what would you do, Mr. Howman, to convert this quantity, 1.547 times 10 to the negative 15 kilograms to grams?
All right, so I got to look at what I'm coming from and going to. So I'm starting in kilograms, and I'm going to grams. And what I can do is I can make a conversion factor such that the quantity that I want to end up with is on the top of a fraction, and the thing that I start with, which is kilograms, will be on the bottom of the fraction.
So I want to start with my grams, or I want to end with grams, and I have kilograms.
On the bottom, yeah.
On the bottom. But I know that there's 1,000 kilograms to 1, or 1,000 grams to 1 kilogram.
And if I think about it here now, what's the value of this fraction, right? Ooh. Because I think what it is that since 1,000 grams is equal to 1 kilogram, this fraction is equal to 1. And so if I multiply anything by this fraction, it won't change the amount. Right. It'll just change the units.
Right, that makes me so happy being a math teacher. We're multiplying by 1. It's awesome. Okay, so now that we have this, so if we take our value, 1.547 times 10 to the negative 15 kilograms, and we multiply it by this conversion factor we created, which is just multiplying by 1, well, happily so, I can see that kilograms cancels kilograms.
And what's left is grams, what we wanted to end up with.
Right. And now I can take this and I can use my calculator. Well, how would you do this question? I can take my calculator and do my calculator, but I can also just do my things from science class. This is a really small number, and I'm going to make it bigger. How do I make this number bigger?
Well, I know it's the negative part of that number that's making it so small.
Right.
And so it's a large negative number. So I bet if that negative number went from like a 15 to a 14 and then again to a 13, right? Now what's happening is this sample is getting larger. The number is getting bigger in effect.
Right. So then could I just make the step that if I'm going to make it larger by 3, the 3 zeros. So I'm going to add 3 to that to get negative 12 grams. Now, would the science teachers be happy with that approach?
Sure, and you could check it with your calculator, I think.
Okay, let's see what we can do. So I can go 1.547. Now I'm going to use this button here, this E. That means times 10 to the power of negative 15. And I'm going to multiply it by 1,000. Oh, one more 0. Okay, and I get what I got.
Oh, there's that negative 12, right? Okay,
negative
good.
12. Fabulous. All right, so that was A part. A lot of work for A part. Now we write an equation to represent this problem. Well, let's duplicate this page and clone it, and then we'll get rid of all the stuff we have so far. We'll clear the ink. Okay, so let's work on this. We want to write an equation to represent this problem.
Yeah, because now I think, for me, I need to draw this out into like a picture or something.
Okay.
There's a lot going on here. There's a bunch of information. It says what? It's like a sample of hydrogen and oxygen has a total mass of 1.547 times 10 to the negative 15th kilograms. So there's a bunch of stuff, and it's made of what? Hydrogen and oxygen.
Right. So I have this stuff here, and it's 1.547 times 10 to the negative 12 grams, because we already
Converted it to grams. Good.
Everything's in grams, so let's keep it in grams. Okay, so and this thing here consists of hydrogen and oxygen. So we have some hydrogens, hydrogens, right? And then we also have a bunch of oxygens, which I'll just do red circles.
Okay, very nice.
Okay, so
next thing. So a hydrogen atom has a mass of 1.67 times 10 to the negative 24 grams.
Right.
So yeah, we can represent this visually. Very nice, Mr. Robs.
Right, grams.
All right, let's do the same thing with, this says now oxygen atom has a mass of 2.66 times 10 to the negative 23rd.
See how I'm color-coding it too?
Wow,
oh, I'm
I
so
like it.
fancy. I'm going out on a limb on this one. Okay, so that's how much one of them costs, or weighs.
Yes. So we got now we're down to this fourth piece of information, right? So the sample has 2.3 times 10 to the 4 oxygen atoms. Okay, so this is the number of atoms. That's the number of like little chunks there that you've got, right? Little atoms.
So I'm going to have to do 2.3 times 10 to the 4, 23,000 of these.
Okay. But we could put a number with that there, right?
Right. We can say that there's 2.3 times 10 to the 4th.
Okay. And then it says how many hydrogen atoms are in the sample, right? So that sort of is analogous or corresponds to this piece of information that we just got. So we're looking for now for the number of hydrogen atoms. So that number we just wrote for the oxygen atoms, we need to find that same number, but of the hydrogen atoms.
So this number, I have all these extra hydrogens, but I don't know, I'll call it X. I don't know how many there are.
You're using the variable there.
My variable X. Sweet. So X is number of hydrogen atoms. So together I know that all these hydrogen atoms and all these oxygen atoms make this. Sounds like some addition happening there.
Yes.
Okay. So if I had one oxygen atom, it would be this much.
Yeah, because I'm looking now, I can see that we could take this, our X quantity of hydrogen atoms and our number of oxygen atoms and put them together and make it equal to this grams. But then we have a problem with units, right? Because we're talking about a number of atoms, and then we have a measurement in grams.
Right. So this is the number of oxygen atoms. This is the grams of one of them. So if I had 2 oxygen atoms, then I would just times 2, right? And that would tell me how many oxygen weight it would be, or mass. So if I multiply this times that will give me the total mass of the oxygen atoms.
Okay.
So if I say 2.3 times 10 to the 4th times 2.66 times 10 to the minus 23, this quantity here represents the mass of oxygen, the total mass of oxygen.
Okay. Should we do the same thing for the hydrogen? Or?
Yeah, let's do the same thing for the hydrogen. So we're going to take the number of hydrogen atoms we have, which is X. We don't know that.
Right, but we can still use that. Even though we don't know it, we now use our variable. Okay.
Right, and I'm going to multiply it by 1.67 times 10 to the minus 24. And so then this is the mass of hydrogen. The two masses together have to be...
Okay, that's our total. Good.
Total.
All right, this is very clear.
7 times 10 to the negative 12. Okay, so now we just have to solve this. And so to do it, let's use our calculator to help us out. I'm going to multiply this with my calculator. So 2.3 times... Oh, let me back that up a little bit. I'm going to use the E button, because it'll keep it in scientific notation for me. And I think it was 10, or times 10 to the power 4, times, and it also recognizes this as one whole number. The calculator does. It knows it's one whole number already.
Right, so you don't need to use parentheses or anything.
Exactly.
Okay.
And then the other value, this one 2.66 E times 10 to the negative 23. And so now I know how many oxygen, the mass of the oxygen atom, 6118 times 10 to the 19.
Wow, that was good. That calculator really was helpful because that was kind of a scary multiplication there if you're not so familiar with these.
Yeah, I wouldn't have a clue how to do that without my calculator. 2.3 times 2.66. Maybe back in grade 4 I knew how to do it, but not anymore. Okay, and so now I have these messy numbers, but it's just really just plain algebra. I'm solving for x. I'm going to subtract this over. So again, I'm going to use my calculator. So 1.547 e to the negative 12 minus, I can just toggle up, hit enter, it'll pull it down. Hit enter, and there I go. I can see now, when I subtract that over, 1.67 times 10 to the minus 24x equals 1.546, oh, let me round that off to 7 times 10 to the negative 12. Algebra says I have to divide by this number in front. And so I'm going to take this value here, I'm going to call it back by toggling top of it, and divide it by 1.67 to times 10 to the negative 24. And I have 9.2. So x is 9.26 to 3 significant figures times 10 to the 11th.
Okay, what was x again?
Good question. X, if we go back, is the number of hydrogen atoms.
Oh, right. Good thing we wrote it down there. Okay.
Right. And when we go through this, let's stop and think if this makes sense. So there's like 9 million billion, a big number, a lot of hydrogen atoms. Are we going to have a lot of hydrogen atoms times this little weight to get this amount? I think that makes sense.
That makes sense.
It's reasonable that it should be a big number. Oxygen atoms is a big number too.
Yeah.
Okay, so there is our solution. Using our calculator just for basic.
Yeah, this was a little bit. I was a little bit frightened of this problem because these numbers were a little bit unusual to me, right? With all of these exponents in there, but really all of the same rules of algebra, they still applied in all the same ways as a simple problem with single digits, right?
Yeah, exactly.
Cool.